Hi everybody, welcome back to Quantum Mechanics. This jazzy music will perk you up. So many good memories of this game. We're gonna listen to Donkey Kong Country music pretty much this week, mostly from the second game because it's so good. What do we got for Administrivia today? First, let's talk about why we're starting late. I went to start the stream at like 4:55, what I usually do, and I hit the button and it just kept saying, sorry, something went wrong, because Google is so great about telling us what's wrong, and I had no idea what that meant, so I just sat there hitting refresh over and over and over. And it eventually worked, but then I had a different issue. It wasn't identifying my stream key. You have to put in a series of letters. It's like a password, but they auto-generate it. You copy it into this program. It didn't have one set, so I was hitting stream and nothing was happening, and I was like, why is this doing a thing? And I was just fiddling around, and I finally figured it out. But everything seems to be working now. I mean, people are talking to me. Presumably you can hear me, and you can hear the music because we're talking about it in the chat. So hopefully nothing will go wrong. I don't really have a backup plan if YouTube just like decides to take a crap one day. I suppose I could stream to my Twitch channel, but that would be kind of weird. And so we'll try and avoid that if I can. But yeah, it's working, so hooray. There's a lab worksheet due this week. It's the Beers Law lab. That's due today. That is a soft deadline. The hard deadline will be tomorrow, so there will be a last call I send out tomorrow for that. And Unit 3 goes forever, so we're not going to have a quiz for quite a while. And then suddenly there's going to be a bunch of quizzes at the end of the quarter, because Chem 161 sucks like that, I guess, in terms of structure. This is where we left off last time. We were talking about orbitals versus orbits. Remember that an orbit is a curve that something would go around like a planet, like the planet orbits the sun. An orbital is a three-dimensional region of space that just defines where we will find electrons by their probability. And we're going to talk about the shapes that those orbitals make later on, but first we're going to assign all the nitty-gritty quantum mechanical details to them. So we defined a bunch of terms at the very end of the lecture last time. We said that these three corresponded to an address of an electron, and this was which electron. We'll talk about why we need to differentiate which electron in just a little bit, because it turns out electrons can pair together by meeting a specific condition, and it has to do with physics. We'll talk about that in a little bit. We have already talked about n. We're going to talk about n again on this slide. N is the principal quantum number, and this is basically an energy level. And so what this y-axis is showing right here is actually the energy, I can't write sideways, of the electron. Now I'm going to further define this by calling this what is called a potential. Again, writing sideways is hard. A potential energy of the electron. What that means is that if you put in enough energy equal to its potential energy, you can move the electron up. So, for example, if we define this right here, n equals infinity, as the electron is separated from the atom, we could call that, okay, to move, if the electron was already here, to move it to this point would take 0 energy. We're going to define that as kilojoules, 0 kilojoules. If the electron was instead down here at n equals 1, I would have to put in this much energy. So what its resting potential energy would be something like this, like negative, I don't know, I'm just going to put in a number, 150 kilojoules. I have no idea what the number is. Off the top of my head. I could go look it up. But so if I added energy to the electron, I gave it 150 kilojoules, I would raise its energy, its potential energy, from negative 150 to 0. So you're going to see an energy diagram in a later experiment, and it's going to be listed with negative numbers like this. And the reason for that is because the principal quantum number measures potential energy. Now, potential energy corresponds to the radius of where the electron is, or in other words, its distance from the nucleus. And so the higher its potential energy, the closer it is to the nucleus. So higher, and I should say the absolute value, so higher magnitude, because all of these are going to be negative. Higher magnitude potential energy means that the electron is closer to the nucleus. Now, when we say higher in energy, right here, be careful. Higher values of N are higher in energy. What this statement is saying is that the values of N will have higher in energy because they will be more positive. Okay, so like this level right here, this might be minus 50 kilojoules. And because negative 150 is less than negative 50, we would say that this is higher in energy. Okay, so this slide on its own can be really confusing later on when I show you the energy scale in lab number 4, which is going to deal with all of these energy levels and transitions between them. Okay, so I just want to make sure that we get the terminology down at the start. Okay. All right. I'm going to have to clear all of this text, so you can pause the video if you need to get that back. Now, the quantum number that we're going to be referring to, the principal quantum number N, has a few terms that are often used to describe it. So another term that comes up is called shell number. The shell number is the number of shells, or in other words, number of layers of electrons that we have populating the atom. For instance, we're going to put electrons in shell level 1 until there is no more space to put electrons in there. There is a given number of electrons you can put in each shell, and that increases because as atoms get bigger, like if I were to draw a picture of an atom, here's the nucleus. Here would be shell 1. You can only cram so much stuff in the space because it's small. Here would be shell 2. It's bigger. You can put more stuff in here. Here's shell 3. You can put even more in there still. Okay? So the shell number is something that we might say, like what electron shell are we in? That would be N equals 1 or 2 or whatever. Another thing that shell number corresponds to is the period. So if you look on your periodic table, you'll notice that your elements are arranged in periods and groups. Periods run across the periodic table, and they're numbered just from top to bottom. So the first row is period 1, and the second row is period 2, and so on and so forth. So if we pick an element out of period 5, for example, it will contain a shell with electrons in shell 5. There will also be electrons in shells 4 and 3 and 2 and 1. But that's also a term that will come up as we start discussing where electrons live. All right, let's talk about the next quantum number. Now that we know about energy level and roughly how far away the electrons will be from the nucleus with quantum number N, we now have quantum number L. Now, this term right here, angular momentum quantum number, not super useful to us in first year chemistry. Angular momentum is a term that appears in an equation that we can use to describe where the electrons are mathematically. For our purposes, what this means is just shape. I didn't mean to highlight the word shape later, but there we go. So the second quantum number will dictate the shape of the orbital. We're going to use other terms for this called subshell or sublevel. And you'll see what this means in a little bit once we start talking about it. But first, let's define what L is allowed to be. N can be any number you want to. As you saw on the previous slide, N goes from 1 all the way up to infinity. This only draws up to 6, because in this space here are all the remaining numbers between 6 and infinity. It's a lot of numbers, so we're not going to cram that in there. But for whatever L or whatever N you choose, L has a specific range of numbers that are allowed. So for a given N, you can have any value of L starting with 0 all the way up to N minus 1. Clear as mud, probably, right? Let's do a little work with this just to show what we're trying to get at here. So remember that N can be any number from 1 to infinity, as long as it's an integer. So if N equals 1, L can be any number between 0 and N minus 1. Well, we already said that N was 1, so this would reduce to this. So L can be any integer between 0 and 0, so the only possible value for L is 0, if N equals 1. We're going to put that in a box because we're just going to separate it out from everything else. Let's go to the next one. For N equals 2, L is allowed to be still any integer between 0 and N minus 1. Well, when I reduce this down, that means that the values of L that are possible are any integers between 0 and 1. So L could be, L could be 0 or 1. We haven't gotten to what this represents yet. This is just going to be pure abstract math here, okay? So don't worry if you're like, well, what the hell does L0 and L1, what does that all mean? We'll get to it. We're just doing the abstract math for now. And I could do the same thing for N equals any number I want to. So for N equals 42, for example, okay, well, L is still bound by the same constraints. We'll plug this in here. That would mean that we could have any value for L all the way up to 40. Oops, not 42. 41. And you can do this for any integer value of N that you want to. Okay? Now, why would you want to? We'll get to that. That's going to be the theme of today is we'll get to that. We're going to do a bunch of really weird shit, and then at some point it will all come together, and we'll talk about it. We'll just go over like what is unclear and hit each nail independently when we get there. All right. So that's how L works. All right. So as an example, what I want you to do is type in the chat, let's suppose that N is 5. What are the possible values allowed for L? And I apologize, my L looks kind of like the number 1. This is supposed to be L. This is an L right here. There you go. So if L is the range from 0 to 4, and I know you can't typeset less than or equal to in there. But so that is inclusive. So that means that we can have any number between 0 and 4 inclusive. So 0, 1, 2, 3, and 4 are allowed. Cool. That's not too bad to do. We can do that. All right. Now, each of these values of L, so those values being 0 or 1 or 2 or whatever, also has a specific letter assigned to it to represent the shape that we're going to talk about later. Here are those corresponding values for at least the first 4 possible values of L. So if L is 0, the letter that we assign to that is S. For L equals 1, that would be P. For L equals 2, that's D. And then for L equals 3, that's F. Now, if you've taken a chemistry class before, you've probably heard these letters before. This is where S orbitals and P orbitals and whatever come into play. Okay. Now, the letters stand for things which are stupid. I think the letters stand for like sharp, principal, diffuse, and fine. And it just has to do with like how intensely those lines show up for these orbitals. S shows up really sharp. P is principal. D is kind of faint. It's diffuse. And then F is very, very fine. You can't see it. Don't worry about the meanings for that. Just remember that these letters correspond to these numbers for L. Now, you can go past L equals 3. At some point, we're going to talk very briefly about how L equals 4 is a thing. But that's going to be in the realm of theoretical chemistry, because later on when we discuss what all these letters mean and how they correspond to things in the periodic table, you're going to see that no element actually has g orbitals or g electrons, because it just doesn't go that far. Our periodic table stops at 118. Maybe someday we will discover element 121, which would be the first element that would actually have a G electron in its configuration. But for now, don't worry about that. Just remember that when you have L equals a number, correlate that number to these letters as shown. And the only numbers we're going to work with for L are 0, 1, 2, and 3. But theoretically, higher L's do exist. All right, so now we have those two numbers figured out. The last number, called the magnetic quantum number, again, that's not a useful term for us in terms of what that means. But what M sub L means is which orientation the orbital is facing. What that means is that for some energy levels and their designated sublevels, there's going to be equivalent solutions to this mathematical equation that works out all of these orbitals. And they're equivalent because we just point them in a different direction. They're all at right angles. They're all orthogonal to each other. Kind of like if you look at the axes on an XYZ coordinate plane and you ask, like, which one is bigger? Well, you can't. They're all the same, right? For the magnetic quantum number, that's sort of the same thing. We have to deal with how symmetry works with arrangements of these equations and the shapes that result from them. And again, we'll show the shapes later. But the important thing that we care about is that M sub L is any number between negative L and L. And those are L's on that screen here. So what I'm going to try and do is I'm going to do this, cursive L, negative L, and positive L. So again, let's go back here and let's play around with this a little bit more, just so we can see what's going on. All right, so again, we'll do this. For n equals 1, what are the possible values of L? Well, we said that L could be anywhere from 0 to n minus 1. And so that means that the only possible value is 0. And then for each of the values of L, M sub L can be negative L to positive L. So this reduces to negative 0 to positive 0. Well, it's 0, right? 0 doesn't get a sign. It's just the origin, right? So for L equals 0, M sub L can only be 0. All right, let's do for n equals 2. And we just said that L could be 0 or 1. And for each of those M sub L's, we can calculate which values are possible for the given L. So just like before, if L equals 0, M sub L is going to be 0. So that's always going to be true. But if L equals 1, M sub L can be anywhere from negative L to positive L, which we would reduce that down to negative 1 to positive 1. Which means that the possible values for M sub L, if L equals 1, are negative 1, 0, and positive 1. And we could do the same thing for any set of orbitals that we wanted to. So if I said, okay, for n equals 3, then the possible values for L would be 0, 1, and 2. Then M sub L would be, well, for 0, the only possible value is 0. For 1, it could be negative 1, 0, or positive 1. And for 2, you could do the same thing. So this would be 2 to, or negative 2 to positive 2. And as L increases, you get more M sub L's that are available. Okay, now all of this on its own is sort of just like trivia, right? It's like, who the hell cares about all this? Like, what does this even mean? So what we're going to do is we're going to take all this information and then later we're going to make it a picture. And the picture is going to make everything come together. Okay. So again, don't dwell on it too much yet. We'll get to it. All right. Let's suppose that you have n equals something. And in that n, we choose L equals 3. What are the possible values of M sub L for L equals 3? And again, these are supposed to be L's. Type them in the chat what the possible values of M sub L are. There you go, good. So negative 3 to 3, inclusive, and all the integers between. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. Okay. So those are the 3 quantum numbers that designate an address of an electron. We'll get to that later on. But for now, the important part is, do we understand the rules? N can be any integer, 1 to infinity. L is any integer between 0 and n minus 1. And M sub L is any integer between negative L and positive L. Because what you'll see on the next few slides are, I'm going to start giving you combinations of quantum numbers. I'm going to say, is this a valid quantum number combination? All right. Now, let's go through and assign terms and descriptions for our Various quantum numbers. So for here, we're going to look at n equals 4. And remember that this corresponds to the shell, or another word that we use for it is level. So now let's look at each of the sublevels. What are the possible values for L when n equals 4? That would be, so remember that L is anywhere between 0 and n minus 1. So we would have 0, 1, 2, and then 3. And then for each of these, we can figure out an m sub L, which values of m sub L are valid. So since m sub L is from negative L to positive L, if L is 0, m sub L can only be 0. If L equals 1, m sub L can be negative 1, 0, or positive 1. If L equals 2, m sub L can be negative 2, negative 1, 0, positive 1, or positive 2. And then for L equals 3, m sub L can be, like we said before, negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. Now, what do the numbers mean for m sub L? Turns out the numbers have mathematical meaning, but we don't care about that in this context because we're not going to be doing math. We're not going to be doing the complex three-dimensional calculus that is needed to plot these out. Instead, what we care about is how many numbers we have written down. So I'm going to highlight each number. And so each of these, I'm just pointing at random ones here. Each highlighted m sub L value corresponds to an orbital. So what that means is that m sub L, each value is a place for electrons to live. And so what you can think of this as is an analogy. So let's just put this on the screen here real quick. So here are quantum mechanical terms for this that you can't see because half of it is hiding behind my thing. There we go. And what we're going to do is we're going to try and plot this out as if it were like a city. So here's my city. And you could split the city into neighborhoods. So maybe here's a neighborhood, here's a neighborhood, here's a neighborhood, and there's some neighborhoods. So if the energy level represents the neighborhood, or the general location in the city of the atom where an electron lives, the sublevel would be the building in that neighborhood. So for example, in n equals 2, there would be 3 buildings. Oops, I'm sorry, there would not be 3 buildings. I'm thinking ahead here, sorry. And then within each building are a number of apartments. And I've off the screen again here. Sorry, hold on. So when the L equals 0 building, there is only one space. And then the L equals 1 building, there would be 3. This is why I wrote 3 before I had skipped ahead. So that's sort of the analogy that we are going for here, is that each of these quantum mechanical numbers represents a different context for our electron. And as we go down the numbers from n to L to m sub L, we get more and more specific about the location we are talking about. N is a very broad sort of like, okay, the electron is in this energy level. L is, okay, it's in this part of the energy level. And m sub L is, okay, it's in this part of that sublevel. So this question on this slide is asking us how many different orbitals are present. So if an orbital is an m sub L value, we'll just count up how many m sub L values there are. And so that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So in n equals 4, there are 16 orbitals. Which means that there are 16 places that we can put electrons in n equals 4. All right, I gotta hit erase so I can make the text appear here. There's everything we wrote out. And there's our total. Now, there is an interesting mathematical thing that comes up here. If you take the energy level and you square it, that equals the number of orbitals. So for n equals 4, there are 16 orbitals because n squared is 4 squared is 16. We could show that for n equals 3 or n equals 5 or whatever. And in fact, on the next slide, I'm going to have you try and do that to show what the 9 different orbitals are for n equals 3. So what I want you to do for this practice problem, I'm going to show you the first one, and I'm going to show you how you write out the quantum number. You're going to write quantum numbers in this sort of pattern. Okay? So we're going to look at n equals 3. And we're going to look at all the possibilities for L. So I want you to write out what the possible values are for L. And then for each of those, write out the possible values of m sub L. So for example, if n equals 3, L could be 0. And for that L, m sub L could also be 0. So the quantum number that we would get for that combination would be 3, 0, 0. Then L could be, also it could be 1, which means that m sub L could be whatever it can be. write out the next quantum number for that. So 3, 1, whatever you get for that. Now, if you have another one that has a different MSL value, just write it different. So whatever number goes here, whatever number goes here, and however many of those that you need. And then do that for L equals 2. And so how many of these different entries should you get? Well, we know that the number of orbitals, each of these corresponds to an orbital designation, because this is our orbital. So we should get n squared of them, so you should get 9 total. Okay, so write out all the quantum number possibilities, and then we'll go over the answers in just a second to see that we're all on the same page, because I realize this is weird. This is the part of the course where things get really weird. All right, I'll see you in a bit. There you go, something like that. And you should have 9 of them, and I think you do. All right, so one more minute, we'll go over the answers. I'm going to clear the screen real quick, because another question is actually hidden under here. We'll come back to that in a second. All right, so let's go through all of the possible quantum numbers. So we've established n equals 3. The possible values for n equals 3 are L equals 0, 1, and 2. For each of those, the possible values of m sub L would be, well, if L equals 0, m sub L must be 0. If L equals 1, m sub L could be -1, 0, or +1. And then for m sub L, or I'm sorry, L equals 2, m sub L could be -2, -1, 0, +1, and +2. So now we're just going to do every possible combination of n, L, and m sub L. So 3, 0, 0 would be 1. 3, 1, -1. 3, 1, 0. 3, 1, +1, which I'm just going to write as 1, like that. And then 3, 2, -2. 3, 2, -1. 3, 2, 0. 3, 2, +1. And 3, 2, 2, +2. So these are our quantum number addresses for our different orbitals, and there should be 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. There you go. So again, let's go over our terminology. There are 9 different orbitals. If I asked you how many sublevels there are, remember that sublevels correspond to L. There are 3 different sublevels because there are 3 different L's. And then if you were asked what level this is, it's just whatever n is. Oh, excuse me. All right, so now that we understand how to make these address numbers here, then the next question is, well, what if I give you a question? Oops, I want to go over here. What if I give you a question that's like this? Here's a bunch of quantum numbers. Now, I haven't written them in the parentheses form. I've just written each of the quantum numbers individually. Which of these numbers shown on the screen is invalid? One of these does not represent a correct address that follows the rules that we've set out for quantum mechanics. So I want you to find which one. We'll even letter them. So A, B, C, and D. Which set of quantum numbers is invalid? And then when I ask you why, I want you to tell me, okay, what rule did we break? So like maybe this number is not allowed for this given set of this number. So tell me which one and type it in the chat. And then tell me why. So if you think it's D, why is D invalid? What part of D fails the quantum rules that we've set up? There you go, that's right. So in the sublevel L equals 1, so if L equals 1, m sub L can only be, oops, I didn't mean to write 0 first. -1, 0, or +1. But this is not one of those numbers. So D is an invalid set of quantum numbers. Now, these rules can be applied to any set of quantum numbers that you want. So I could write something like this. And I could say, is this valid? And you would go, okay, well, is L a value between 0 and n minus 1? It is, so that's fine. Is M sub L a value between negative L and positive L? It is, it's fine too. Okay, so you might see randomly large numbers on the quiz because I throw a few of those in there. And just follow the rules. Don't worry about, oh, what orbital or what atom does this represent? It doesn't represent an atom. But these all do theoretically exist, so we want to apply the rules to them. All right, let me know if you have any questions. I'm sure that there are a lot of like nebulous sort of, huh? Why questions. But again, we'll get to it. All right. Now, when we get to the shapes of orbitals, I kind of wish this came a little bit later in the slides, but it doesn't, unfortunately. When we get to the shape of the slides, we're going to care mostly about L here, but N and M sub L do affect this a little bit. So what we're going to do is we're going to first look at each of the individual... Well, I guess we're first going to look at L equals 0 and show what that impacts when you have N equals whatever. So let's look at L equals 0. L equals 0 is the s orbital. You remember that we assigned the letter s just arbitrarily to L equals 0. When you plot out the equation for these orbitals, and I can show you the equation during the break. I'll go get it. It's miserable, which is why we don't look at it. The shape that you plot out looks like this. It's just a sphere. Because it's an orbital, remember, orbitals represent a region where electrons can be. So the electrons can be anywhere in this circle, or in this sphere. It's a three-dimensional entity. So my electrons could be on the surface, or they could be right near the middle, or wherever. They are just sort of buzzing around all over the place however they want to. Now, because energy levels get bigger, as n equals 1 is the lowest level, n equals 2 is bigger than that, and n equals 3 is even bigger than that, if I increase the n value, my orbitals get bigger. So for 2s, the orbital would be larger than 1s, and for 3s, it would be even larger still. So for each of these orbitals, we could write an address. So this would be 1, 0, 0. And this would be 2, 0, 0. And this would be 3, 0, 0. Now, the important part, remember, L dictates the shape here. So all spherical orbitals, which are s orbitals, will have an L equals 0. And because m sub L has to be between negative L and L, m sub L for an s orbital will always be 0. We're not going to worry about that just yet. M sub L will come into play when we get to the next L, which will be the p orbital. Now that's simple enough. Okay, an s orbital is a sphere. Sure, I can remember that. I wish it was that simple. Because remember, we determined earlier when talking about electrons and exploring their properties that electrons are both particles and waves. So the orbital is the wave representation of our electron. And as waves get more complicated, as you increase n, what did we add to it? For example, n equals 1 as a one-dimensional wave looked like this, right? That was n equals 1. But n equals 2 as a one-dimensional wave looked like this. And what did we start encountering in higher energy waves. I'm putting big dots on these just to... What were these things that we encountered in one dimension? There was a... Oops, I hit mute on accident. There's a special word for it. What was that word that described those dots that I put on the wave? They're nodes. Very good. So if waves in one dimension have nodes, surely waves in 2 dimensions and also 3 dimensions would have nodes too. And we saw the 2-dimensional nodes where we had that plate that we hooked up and poured sand on it, and then the crazy like trance music played in the background. For 3-dimensional orbitals, this is still true. So if we were to slice open this orbital, what we would actually observe is something like this. So this is the 2s orbital, and the color represents the likelihood of you finding the electron. So the center is very, very blue. So there's a high probability of finding the electron here. And then the outside is also very blue. So there's a high probability of finding it there too. But you'll notice in this region right here, there's sort of a dead zone. And that dead zone is the node. So a 2s orbital is not just a bigger sphere. It's actually a second sphere around the first one. And between the 2 spheres is a node. And what a node represents is, hey, it takes an infinite amount of energy to move the electron here because it's a node. And because infinite energy isn't practical, we never find the electron at the node. And this is true for all s orbitals. There will always be n-1 nodes per orbital. Now, specifically, these are radial nodes, because they are some radius away from the nucleus. And I think on this, yeah, here we go. On this slide, what I have is the probability of finding an electron based on its radius. So r is the radius. This is just a fancy term for how likely you are to find the electron at that spot. I'll tell you what psi means during the break, because that's beyond the scope of this class. And so what that means is that if I'm probing for the electron, I will never find it at the node, which is a fixed distance away from the nucleus. So the nucleus is at the origin here in all of these cases. Now, in a higher level chemistry class, you'll care about this a lot more. But as far as we're concerned, for just understanding what the shapes of orbitals look like, it's important to know that nodes exist. And that there are certain spots in your orbital that you will not find an electron. So there will always be n-1 nodes. For an s orbital, there's only radial nodes possible, so all the nodes are radial nodes in an s orbital. But for other orbitals, we're going to introduce planar nodes. And planar nodes will occur when you have L greater than 0. So the total number of nodes will be n-1, like we said. But once we start adding L in there, we're going to start seeing planar nodes too. And I'll show you what that means when we get to p orbitals. So that thing that I've underlined again, that looks like the number 1. We're going to just do this to it, so it looks like an L. All right. Now let's look at the p orbital. In order to have a p orbital, we have to have L equals 1. So for n equals 1, L can only be 0. So you can only ever have a 1s orbital You can never have 1p. That's not allowed because you can't get L equals 1 for n equals 1. So the first instance of an L equals 1 occurs in n equals 2. What does that look like? Let me erase this text that I've written, and we'll just show the pictures on the screen. A p orbital looks like a bow tie. Some people call it a dumbbell. That's fine too. Now, if you slice open the p orbital, what you'll find is there's no nodes inside. There are no radial nodes, but remember, there should always be n minus 1 nodes, right? So there should be one node somewhere. And for p orbitals, the node that you get is a planar node. In this orbital right here, I've labeled it pz. It's called pz because the orbital goes along the z-axis. But interesting about that, we have a planar node. So all along this xy plane right here is my node. So the xy plane is the planar node. What that means is that for specifically this p orbital, the electron density can only be along the z-axis and a little displaced from it. You can never have any electron density on the xy plane itself. So at z equals 0, you'll never find an electron. The same thing exists over here. So this is the yz plane. I'm trying to color it specifically so you can get the representation of the plane here. So this would be the yz plane. And then over here we have the xz planar node. So that would be this side, and then this is in front of it. And so that's our node in 2p. There is a planar node and no radial nodes. Now, why are there 3 of them? If you remember, for L equals 1, the possibilities for M sub L are -1, 0, and +1. And we said that M sub L represents an orientation. So what that means is that there should be 3 possible orientations in L equals 1, and these are what those orientations are. And so each of my numbers corresponds to an orbital. Now, do the numbers correspond to a specific orbital? No. And the reason for that is because I could label my axes however I want to, right? Why does the z orbital or the z-axis have to go up and down? Could I label that y? Sure, I could do that. If I did that, then the orbital on the left would not be pz, it would be py. But because there are 3 different possibilities, they are all assigned different quantum numbers that are based off of whatever orientation of axes I choose. So the takeaway is that we don't really care about these numbers. -1, 0, and 1 don't really care. What we care about is that there are 3 of them. And so there will be 3 different orbitals. Again, the value of M sub L that is assigned to the particular orientation is totally arbitrary because you get to define it. You can choose whichever orientation you want for X. And when you do that, and you do the math, the results will work out, oh, this number will be one axis, the other number will be a different axis, and then the third number will be the other axis. All right, so that's our 2p orbital because we're looking at just 2p here. This slide talks about the planar node. So again, for this specific orientation, for 2p, we would have n minus 1 nodes. And we have a planar node along the xy plane right here. Now, what if we had a 3p orbital? What would happen? What would that look like? Can we combine everything together? Let's do an example. So if I had a 3p orbital, we know that there must be n minus 1 total nodes, and that there must be n minus l minus 1 radial nodes. Any other nodes that are left over must be planar. So if there is a 3p orbital, there must be 2 total nodes. And if it's a 3p orbital, if this number is 3 and this number is 1, 3 minus 1 would be 1 radial node. And so what's left over must be 1 planar node. So now we can draw something that represents that. Well, we know it's a p orbital, so it's going to look like this, right? But it needs a radial node. So for 3p, I would just draw a bigger balloon around it. And then this would be my node. And then if I was going to put coordinate axes over this, I could say that this would be the z-axis. Here would be my x-axis. This would be my y-axis. And you could see the planar node that would go in this space around it. So there's my radial node. We'll actually label it that. And there's my planar node. All right, so those are the shapes of s and p orbitals. We are due for a break. I did go a little bit longer, so digest that for about 10 minutes, because this is weird, but we're gonna get to the point where it all comes together by the end of the lecture. So let me put the timer up here. We'll take a 10-minute break, go fill your water, take a breather, listen to some more Donkey Kong Country 2. See you in a bit. Oops, I'm just sitting here listening to the music and not paying attention. That's one of the best songs on the soundtrack, though. Alright. Where are we? Alright, so let's continue our discussion of orbitals. I'm going to put the pictures of the d orbitals on the screen here. And the only thing I'm going to say is that all of the calculations with all the nodes still do apply, but you're going to notice something kind of weird here. Like, what the heck is this? Where's my planar node in this guy? And I don't actually have a very good answer for that. As you get to d orbitals and then f orbitals, the shapes get really weird. All that we're going to care about for d orbitals, because we're not going to do anything with d orbitals in this class. D orbitals are inorganic chemistry in like 300 level class, and then F orbitals are just like, who the hell cares? And I say that as somebody who did specifically chemistry with elements that have F orbitals, but there's a specific reason for that we don't care about F orbitals. So I'm just showing you the shapes to show that, oh, there are 5 different shapes, but the math starts to get really crazy here. And so we would say, okay, well, if L equals 2, M sub L would be -2, -1, 0, +1, and +2. And so there are just 5 different orientations. One of those orientations is very weird. That's this one. And it has to do with complex calculus that I don't understand. I've never studied that level of physical chemistry, so I don't know. And then for F orbitals, it's even crazier. Like, there's even more ridiculousness here. Like, where does the little donut thing come in? I don't know. I don't know how to answer that. But what we can say is that for L equals 3, M sub L would be -3, -2, -1, 0, 1, 2, and 3. And that checks out. So again, you don't need to memorize these orbitals. We don't care about D and F. The only things that we're going to care about in this class are S and P. I'm just showing you the D and F orbitals because they do exist. But for our purposes, we just don't really care about them that much. Okay, so what I want you to do is I want you to try and draw a 5s orbital. Is there another question on here? Yeah, I want you to try drawing a 5s orbital and a 5p orbital. Don't worry about the orbital probability graph. You don't have to worry about that. But just try and draw a picture of what 5s and 5p would look like. Make sure you count the nodes correctly. Put the correct types of nodes in. And then we'll compare your answers with mine in just a second. I'm trying to find the Schrodinger equation. I didn't realize that that was on the screen here. So all this crazy... Oops, that's not... All this... Where is it? Now I don't know where it went. Anyway, I will figure that out. Sorry. What you were seeing all those crazy equations for was what I'm going to talk about in the next section. So I apologize for that, if that popped up and blocked your view of the screen. All right, 1 more minute to finish your sketch. All right, let's draw these orbitals. So for a 5s orbital, remember that there are always n minus 1 total nodes. And then there are n minus L minus 1 radial nodes. Well, for 5s, n is 5 and L is 0. So that would mean that there are 4 radial nodes. So what I should do is I should just draw a really big orbital. So there's my 5s orbital. Oops. Let me try that again. There we go. That's better. And I should put 4 nodes in it. So 1, 2, 3, 4. Sure. There we go. So something that looks like that. And so here would be my nodes. 1, 2, 3, 4. The outer boundary is not a node. That is just the boundary of the orbital. It looks stupid, but that's the best way that I can think of to draw it. All right. For a 5p orbital, same rules apply. Actually, what I'm just going to do is I'm going to go like this. We're going to erase this and put p here. And we'll just erase this. Actually, that's silly. Why don't I do it this way? There we go. Uh-oh. Why? Oh, because I got to do that. There we go. All right. For a 5p orbital, n is still 5. L is 1 now. 5 minus 1 minus 1 would be 3 radial nodes. The last node, so this would be, there's 4 total nodes. So there must be 1 planar node. And for any p orbital, you just go like this. Drawing off the screen if necessary, you know. And so this would be my planar node in the xy plane. And then I'd have 3 radial nodes. So I would do 1 node, 2 nodes, 3 nodes. There you go. That's good enough. So that's what a 5p orbital would look like. Now, I should have done this with the s orbital, but another way of looking at it could be like, oh, here's 2p, and then we'll put a 3p around it, and then we'll put a 4p around that, and then there we go. So if that helps you to just like shortcut to draw the orbitals, or at least recognize them, because I can't make you draw on canvas. Like that's not a thing that I'm going to make you do. You're going to have to identify pictures if you have to do this at all. All right. Now, the last little bit, which is why I was fishing around for this equation here. Let me get this window capture on the screen real quick. I've been dodging, like, the math behind this. So, oops, I need this part over here. Oh, no, wait, that's it right there, I guess. Okay. Is that the tab I want, actually? No, it's not. I want this one instead. I found a better one that represents what I want. All right. On the screen are the equations that govern how to calculate these orbitals. So these are functions of radius, which is r, and then 2 different angles. There's an xy angle and an xz angle. So that's what theta and then phi are for up there. And you see that those start appearing in the equations as you get to more and more complex stuff. This is ridiculous. That's all I have to say about that, is this is ridiculous. And you have to integrate these in 3 dimensions. For us, integrating in 2 dimensions is hard enough, doing a 2D or XY plane with a graph. If you've taken Calculus 2, you've done integration, and that's difficult, right? It's even worse in 3 dimensions. So this is why we don't care about the math at this level, is because it's too hard. There's just too many terms, and we don't want to deal with that shit, so goodbye. So I have given you the shapes that are the output of those equations, and that's what you've been seeing so far. And when we input the various quantum numbers, n, l, and m sub l, those are the shapes that get spit out. Now, these slides are not very important for our purposes because we're not going to actually do MO theory later on where we would care about phases. But because those equations that we had on the screen here they are again, boop, boop. Those equations have positive and negative components to them. I can represent that as a picture right here. If I have a wave, the top of the midway point would be a positive number, and the bottom would be a negative number, right? Depending on how many nodes I have, I could have both positive and negative solutions. And so we refer to these as phases. of the wave. Now, what do we care about that? Well, when we plot these in 3 dimensions, this is what happens. For our S orbital, we can only have one phase at a time. It will either be positive or negative, whatever our solution is. Note that this is a value and not a charge. We haven't even talked about charge yet. For a p orbital, there's a node in it, so you could have a positive part and a negative part. And one half has to be the positive part of the equation, and the other half has to be the negative part. If we were doing MO theory in chapter 5, this would be important because what we would be doing is adding orbitals together. Because you could take a p orbital and add it to a p orbital, and then if the phases match up, you get something that looks like this. Whereas if you tried to add something where the phases didn't add up, they would cancel. And I'm only bringing this up because in case you do touch on molecular orbital theory in organic chemistry, or in P-Chem or later on, hopefully you'll remember, oh, Wes talked about phases. Because that's really all we talk about here, is that's the level of phases that we go to. And so, again, you just need to know phases exist. Will it be important for this class? No. It says we'll talk about it in chapter 5, but we actually skip this, because every other instructor skips MO theory, because there's just too much content in 161 for us to cover it. Which is unfortunate, because MO theory is really cool. Okay. We have talked about the first 3 quantum numbers. It's time to talk about the last quantum number. The last quantum number is called the spin quantum number. And the spin quantum number relates directly to electrons themselves. For an orbital being like, say, the 1s orbital, I can put 2 electrons in there. And you might think, well, that doesn't make much sense, because electrons repel each other, right? Well, it turns out that's not the entire story. So, electrons would repel each other based on their charge. They're both negative, so negative things would repel. However, there is also a magnetic component to all things that are charged. If something is charged and it's moving, and we saw this with the cathode ray tube, we had electrons moving past a magnet. The electrons bent. And depending on which orientation of the magnet we use, they bent in a different direction. This suggests that electrons also have their own magnetic field. And that magnetic field is generated by the fact that they are rotating. Because electrons rotate, they make themselves a magnet. And if I have electrons rotating in opposite directions, they make opposite polarity magnets, which then attract. So even though electrons would repel each other, if their spins are different, they will attract just enough that we can pair them together. And this is called the spin quantum number. So what we do is we designate electrons as having either spin up, which we give them the quantum number plus 1/2, or they are spin down. They have the quantum number minus 1/2. And all this says is that, okay, in my orbital, I can put up to 2 electrons. One must be spin up, the other must be spin down. So when I write my address now in this form, there's a 4th term that we add to the end. And that represents which electron in the orbital. Will it be the one that is spin up or spin down? Now, spin up and spin down are arbitrary, because you just flip the entire system upside down, and then they would flip, right? Or you could flip it sideways, and then they're left and right, or whatever. So, for our purposes, we're always going to categorize spin plus 1/2 as the up electron, and spin minus 1/2 is the down. And so I've represented them as these arrows like this. And that's going to be relevant in the next section where we start drawing these in a diagram. Now, because electrons always have energy, they're always rotating and translating, they always have spin. So every electron will have a spin quantum number assigned to it. But the value that is assigned, again, is arbitrary, because I could just rotate the system. So what this means is that for any orbital, as long as the electrons have opposite spin, you can pair them together. And there's a special term for this. This is called the Pauli exclusion principle. And the rule is you can never put two electrons in an orbital if their spin is the same. Now, this is worded very specifically. And the reason for that is, let's suppose that I have an orbital like this. If I try and do this, this is not allowed. They would repel from their charge and their magnetic pole. Same thing that would happen if I put two down. That would not work. I have to put them opposite spin. Now, if there are only two spins, why do we care? Why did we word it this way? Well, what if the possibility of other spins exists, and we've just never detected it? So the wording is set up in such a way that it allows that possibility to exist. Because we've never observed a third spin doesn't mean that there isn't one out there. And in fact, you may be asked a question about, oh, what if there is theoretically a third spin? What would happen? And you can answer that because the Pauli exclusion principle specifically says you can arrange your electrons however you want to, but no two spins can ever be the same in an orbital. All right. And I think that is everything that's the end of this section, right? Okay. So this question down here we've already talked about. This is just n squared equals the number of orbitals. But what I'm going to do is I'm going to go through n equals 4 in the last few minutes that we have. We didn't quite get to electron diagrams, which is unfortunate. Because that's really the thing that ties all this together. All right. So earlier we wrote down all of the possible quantum numbers for n equals 3. Let's do that for n equals 4, just as a sort of summary here. So what are the possible values of L for n equals 4? L can be 0, 1, 2, or 3. And then M sub L for 0 could be just 0. For 1, it could be -1, 0, or +1. For 2, it could be -2, -1, 0, 1, or 2. And then for 3, it could be -3, -2, -1, 0, 1, 2, or 3. Talking and writing numbers is hard. And then for each of these orbitals, because remember, this is an orbital, 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 orbital. All of those are orbitals, so we should have 16 of them, and there is. For each orbital, you can have m sub s is either plus or minus 1/2. So if there are 16 orbitals, and I'm allowed to put 2 electrons because I could either have +1, oops. I keep writing plus or minus here. Since I can have either a plus 1/2 or a minus 1/2 or both put into an orbital, how many total electrons would there be? Well, in this orbital, there would be 4, 0, 0. Positive 1/2 would be a valid electron, or 4, 0, 0, negative 1/2. So for each orbital where I could write the quantum address, I would then append either plus 1/2 or minus 1/2 to it. Now, I'm not going to go through all of these examples because we could write out all 16 of them. Like I could do 4, 1, 0, 4, 1. I forgot negative 1. I probably should have done that first. We could do each of these, and then for each of these, we could write the fourth quantum number there too. So if there are 16 orbitals, and I can write 2 different electron quantum numbers with the plus or minus half per orbital, there must be 32 total electrons in n equals 4. All right. You could do the same thing for n equals 5. You would need to invoke g orbitals for that, but we're not going to do that just as because it's this but more. All right. Is it? Yeah, we're past time. So that's all we're going to do today. I realize that this is all going to be stupidly just overwhelming. And this next section is what's going to start to tie stuff together, because what we're going to do, just as a preview here, we're going to start taking these electron addresses, and what we're going to do is we're going to make them into diagrams that look like this. And so you could probably see that, oh, okay, well, here's my 1s orbital. This is n equals 1. Here's L equals 0. Here's L equals 0. L equals 1. And then each of these boxes is an M sub L for that. And we're going to start building this diagram and then dropping electrons in it following the Pauli exclusion principle. So our first electron would go here, and then the second electron would go here. Third, fourth, 5, 6, 7, 8, 9, 10, and so on and so forth. So that's where all of this is going to start to come together. But we're not going to do that today because I'm not going to be able to get far enough for it to be of any use. So we'll start that part on tomorrow. I was thinking about what class I almost said Thursday, but this is a Monday, Tuesday, Wednesday class. Okay. So I want to thank everybody for coming to the lecture. Don't panic if you feel like this is a bit overwhelming. Ask me questions in the Discord or over email. I'm more than happy to answer them. As we go through this will start to congeal together. And the deeper in we go, the more sense it will make. So I hope that at least at this point you have a grasp upon the basics, because I realize that this is very, very difficult. I think this is probably the hardest part of chemistry 161 all the way through 163, is just getting a hand on this. And there's going to be a little irony to it later after we finish the next section tomorrow. So we'll see you for that. Have a good night and stay warm.